Hey viewers, welcome back to our channel. Hope you are doing extremely well. So today we are going to discuss another interesting question on the topic of binary tree, that is nothing but bottom view of a binary tree. So without wasting time, let's move on to the question. In this question we are provided with a binary tree. Let me create some binary tree. So here I'm assuming 3, 1 and 6. Okay, here 0, 2, 5, 10, 4, 15, 9, 11, 12, 13 and 14. Okay, so here we are assuming that we are provided with this binary tree, and what we need to tell is that we need to assume that some person is looking at this binary tree from the bottom. Okay, and we just need to tell that what are all those nodes which will be available to the viewer. Okay, which all nodes will be the user see it. Okay, so the first thing is that what are all those nodes which the user will be able to see. Those nodes will be nothing but 6, 4, sorry, not 4, 13, 12, 14, 10 and 11. So these are all those nodes which the user will be able to see when he start looking at the binary tree from the bottom. Okay, this 6, 4, 6, 13, 12, 14, 10 and 11. All the other nodes, all these other nodes get hindered by or get hidden by any by the other nodes. Like let's have a look at this 2 and 5 combination. This 2 and 5 are actually overlapping each other. They are fighting with each other to come at the same position, and when they resolve their problem, like I'm assuming that at first 2 will come and after that 5 will come. But the moment they resolve their conflict, they came in back-to-back lines. Okay, they came in a single line, but the last node of that line is nothing but this 12. So when the viewer start looking from the end, the first node he will be able to see is nothing but this 12. This 2 and 5, both of this node get hindered after this 12. Okay, so I hope you get it, that why we are not able to see all the other nodes, why the viewer only be able to see only these nodes. Okay, he will only be able to see these nodes. So that's all for this question. I hope you get the question. So let's move on to the intuition part, like how we will solve it and what are the intuition part of this question. So the prerequisite for this question is nothing but the vertical level order traversal. Okay, vertical level order traversal. If you haven't watched that video, please go and watch that video, because the whole concept of this question is actually based on the vertical level order traversal. Means we will a little bit work the concept of the vertical level order traversal, and we will get our required output. And the another prerequisite for this question is width of the binary tree. Okay, width of the binary tree. Both of these questions are the prerequisite for this question. So that's so yeah, so let's move on to the vertical level order traversal, and let's try to understand that how the vertical level order traversal help us to achieve our goal. Okay, so what is the vertical level order traversal? First, let me write it. Okay, so the vertical level order traversal, we know in the vertical level order traversal, we just return a vector of the vector. Okay, 0, 1, 2, 3, 4 and 5. So in the vertical level order traversal, we know that we will create the lines like this, and each line will show a particular level. Okay, we already knew it. So these lines are doing nothing, just representing one of the level. And let me perform indexing for each level. It is residing at level -0, it is residing at level -1, -2, 1, 2, 3. Okay, so these are the indexing. And when we try to when we start storing these values into the vectors, we know that the vector indexing start from 0. So we need to map this -2 into the 0 as the first index, and this 0 as at the 2 to make it to store it suitably. Okay, now moving further. Okay, moving further, here we can see that when we try to store the vector vector at the particular positions at each index, here at the each level there is a vector which stores all the values which lies at that particular level. That is, for the index 0, or for the level 0 the value 0 will come. For the level 1, 1, 11 and 13 will come. For the level 2, 3, 5, 12 will come. For the level 3, 6, 15, 9 and 14 will come. For the level 4, 10 will come, and for the level 5, 11 will come. Now you might be thinking that how this vertical level order traversal help us to achieve our top bottom view. Now I'm going to say the one thing. Okay, what is the bottom view? Is that when you start looking at our binary tree from the bottom, means the values which lies at the end of the particular each level. Okay, so here you can see that our when we start looking at this tree from the bottom, we get our output like this: 6, 13, 12, 14 and 10 and 11. And what are the last values of each level here? Here also, okay, it was not 6, it was 0. Here also at the each level we get the values like 0, 13, 12, 14, 10 and 11. So I hope you are getting that what we need to do in this question. We just need to store the vertical order traversal here also, but this time we don't need to create the vectors of vector. We just need to store each value for each particular level. Okay, so let's have a look at the deep intuition of it with the dry run using the Q data structures. Okay, we are going to use the Q data structure to have a better dry run of it. And we know that this time we just need a single vector having the indexes like this: 0, 1, 2, 3, 4 and 5. Okay, and each index shows the level at which we are working on. Okay, at first we will put the root in our queue. So we put this 3, we remove this 3, and we just map this value, this 3 at its respective level, that is at the level number 2. So we store its value at here, that is 3. We store here the 3. Now we add its children, that is we add this children, that is 1 and 6. We add this. Now we remove the 1, we store this 1 at its respective level, we store 1 here, and we add its respective children, that is 0 and 2. Again we remove 6, we added this 6 at its respective level, that is we add here, and we add its children, that is 5 and 10 into our queue. Now again we remove this 0 from our queue, we add this 0 at its respective level and add its children, but here you can see 0 don't have any children. Now working on the 2, we remove this 2, but here you can see the 2 lies at the level number 3. Level number 2, okay, 0, 1, 2, yeah, 2 is lying at the level number 2, but at the level number 2 there is already some position. What we do here, we just update that position. Okay, we just remove that position, we update it with the value 2. Similarly for the 5, we update it with the 5, but earlier we update the 2 with the 5, but earlier 2 don't have any of the children, so we haven't added anything here, but the 5 have some children, so we need to add them also. So we add 11 and 15 into our queue again. Moving forward, after this 5, we remove this 10. Okay, 10 is lying at the level number 4. Okay, so we have added the 10 successfully. Moving to the 11, we add the 11 at the level number 5. After, okay, yeah, 10 have some children and we just forget to add them. So 10 has some children, that is 9. Okay, so let's remove this 9. We reaching to this 9. This 9 is residing at level number 6, level number 3. Okay, 9 is residing at level number 3, so we need to update this 6 with the 9, and as 9 have some children, we need to add them. 9 have 12, so let's remove this 12. 12 have some children, that is 13, 14. Let's add them and update the 12 at the level number 2. So we update 12 here, and 13 and 14 update the level here and here and here. Okay, so I hope you get the dry run of this question. So you can see that at the last, what we get in the vector, we just get the required answer, that is all those nodes which are lying at which the viewer will be able to see when he start looking at the tree from the bottom. And how we able to achieve it, we are actually just able to achieve it with the help of vertical level order traversal. So let's move on to the Pepcoding website and let's try to code it. Okay, so this is the bottom view function. Before working on the bottom view function, we need to create some helper function, that is nothing but the width function. So void width. One more thing is that I'm not going to explain the code of the width function, just because there is a dedicated video which lies on the YouTube channel of the Pepcoding. So please go and watch that video. And actually, the vertical level or the traverse and the width, both the concepts are very important for this question. If you haven't watched that video, please go and watch that video. Okay, unless and until you will not watch it, you don't get the concept or the deep intuition of this question. Okay, so root int hl shell and vector int reference answer. Okay, reference answer. Now let's complete this function. If root equals to null pointer, what we'll do, we just return. Otherwise, what we'll do, answer 0 equals to min of hl comma answer 0, and answer 1 equals to max of hl comma answer 1. Okay, now let's make some recursive call with root left hl minus 1 and answer. Okay, similarly with root right hl plus 1, as we are making a call toward the right hand side, that's why we need to update the hl plus 1. That's all for this width function. One more thing is that we need to create a pair. Okay, why we need to create a pair? In the Java, there is no such pair data structure, so there we create a pair class. But here in the C++, there is an STL which consists of the pair data structure. That's why we are using the pair. Okay, we are just taking help of it. Tree node comma int hl and pairs. And let's complete the code of bottom view function. Okay, so what we'll do, at first we create a queue of integer tab, pairs tab, sorry, not the integer tab, queue of pairs tab, and let me rename it queue. Okay, now creating a vector of integer type of size 2 and naming it as min max of size 2. What it stores, it will help me to calculate the length. Okay, so let's recursive pass this vector into a width function with some parameters min max. Okay, now calculate the length min max 1 minus min max 0, min max 1 minus min max 0. And now at last let me create a answer array. Okay, vector int answer. Now one more thing is that we need to let me add some default values of the length size in my array. Size less than equals to length, then equals to length and I plus plus, and answer dot push back int 1e9. so I'm putting the extreme value of the integer into as a default value in my answer. Okay, now let's put the root into my queue data structure, queue root minus min max of 0. So now let's complete two loop, that is int as equals to so QUE dot size is greater than 0. Okay, now at first let me remove the front value from the queue data structure. Pairs rp equals to QUE dot front. Now q dot pop, and let me update each time, update the value at my answer array list for each level. Okay, so that the moment I reach to the last point, I am accessing on the last node at each level, that value gets stored in my answer array list. Okay, so rp dot first well. So one more thing, if p dot first left is not equals to null pointer, if such a case arises, I will perform something here. Similarly, if rp dot first left, earlier we were working on the left, this time right, is not equals to null. Here also we perform some work. So what work will do, we just need to add or push into my queue. Okay, wait, push here, and before pushing we need to create a pair, and rp dot first dot left and rp dot s c o and the second swan. Q dot push rp dot first dot, okay, first node right, st first dot right, and rp dot second plus one. So that's all for the code. And at last, what we'll do after returning from coming out of this while loop, we just need to return the vector of answer, retur, and return answer vector. So that's all for the code. If we encounter any of the error, we'll just try to resolve it, and let's try to submit it. We get the error. Let's look at the error we are getting. So the first error was this. Yeah, here and this is just because I missed to write this. Okay, I just forgot to complete the statement. Okay, yeah, it is accepted. Let's try to submit it, and that's all for this video. I hope you get it at how the vertical level order traversal help us to achieve the bottom view of a binary tree, and at last we get the full marks, means this solution is accepted for all the test cases. I hope you get the intuition of this question. I hope you get the problem statement, the solution of this question. So that's all for this video. If you like this video, hit the like button, share it with your friends, and let's meet in the next video. Till then, stay safe, stay healthy.